So we just did a little demonstration on standing waves. But before we really understand standing waves, we've got to understand a concept called the resonance first. Resonance is a phenomenon whereby a vibration can grow. A vibration grows when there is a disturbance set at a very particular frequency called the resonant frequency. Probably everybody in this classroom has walked across the bridge, the pedestrian bridge in Okotoks. Is there anybody that hasn't walked across that pedestrian bridge behind the library in Okotoks? No? Okay. Have to do that sometime. When you walk across that pedestrian bridge in Okotoks, you know that if you jump, you can cause that bridge to start bouncing a little bit, right? To start vibrating a little bit. That bridge has what we call a resonant frequency, a very particular frequency at which it wants to vibrate. Everything has a resonant frequency. Everything has a natural frequency at which it wants to vibrate. So we'll define that as a natural frequency at which something wants to vibrate. We'll say wants because can't really want anything, but the natural tendency is to vibrate at this natural frequency, this resonant frequency. The bridge in Okotoks wants to vibrate at a particular frequency. Your guitar string wants to vibrate at a particular frequency. This meter stick, when I put it on the desk and then pluck the meter stick here, wants to vibrate at a particular frequency. A pendulum, when you take a pendulum, a swing set or whatever, and you pull back the pendulum bob, it wants to vibrate at a very particular frequency. Everything has a natural frequency or a resonant frequency at which it wants to vibrate. Resonance, the phenomenon of resonance, occurs when there is a force applied when there's a force applied on something at the resonant frequency. In other words, if the resonant frequency of the swing set is 20 hertz, and you apply a force 20 times per second, then resonance occurs. That disturbance will grow. If the natural frequency of the bridge, the pedestrian bridge in Okotoks, is 10 hertz, let's say, it's not that high actually, it would be lower than that, but let's say it's at 10 hertz, and you apply a force at a rate of 10 cycles per second, then you can cause that disturbance to grow. In other words, you push the swing set at its natural frequency, you cause the swing to grow higher and higher and higher. The disturbance grows bigger. If you jump on the bridge at the right frequency, then you can cause that vibration that you felt on the bridge to grow higher and higher and higher. There was a bridge in Tacoma, Washington, I can't remember the exact year. It was probably about 60 or 70 years ago, called the Tacoma Narrows Bridge. It was only up for a few months. It was this suspension bridge that went across this channel of water, and it was pretty long. Okay, and it was built. It wasn't designed really well at all. Just after it was open, people noticed this bridge would sway, and that's a little bit of swing's okay. Bridges are designed to move. They have to be able to move. If they're brittle and a big wind comes up, what happens? It snaps, right? It literally breaks. Okay? We don't want that to happen, so it's okay to move a little bit. When people were noticing, though, these vibrations that were bigger than they should be, bigger than they had noticed on other bridges before. What happened one day, about 6 months after this bridge had opened, the wind was gusting. It was gusting at a very particular rate, corresponding to the resonant frequency of that bridge. What happened to the bridge? The vibration started growing bigger and bigger and bigger, till the bridge was doing this. And then what happened to the bridge? It collapsed. It literally broke apart. The concrete broke apart because the vibration was getting too big. Okay, if you push on your little brother or sister on a swing set at a random frequency, here's the swing set. Okay, you push at a random frequency, and nothing really happens to your brother or sister, right? Your brother, okay, you're swinging a little bit, but there's no real growth and vibration of that swing set. But if you produce, or if you push at a very particular frequency, the resonant frequency of the swing set, what happens? The vibration grows bigger and bigger and bigger, right? So resonant frequency is the natural frequency at which something wants to vibrate. Resonance is this phenomenon that occurs whereby the disturbance grows because you apply a force at the resonant frequency. That make sense? Now the demonstration that we just did here with standing waves is related to this phenomenon of resonance. Okay, I showed you literally standing waves that were being produced in this string. Standing waves are waves that appear to be standing still. Really, the waves are standing still. The string isn't, but the waves are standing still. They're produced by the interference of waves that are going one way with the interference of waves that are coming another way. And they occur only at very specific frequencies, as you saw in the demonstration. Those frequencies that they occur at, in the demonstration, it was 4, it was 8, it was 12, it was 16 hertz. They occur at resonant frequencies, natural frequencies, just like this set of keys here, the swing set, has a natural frequency at which it wants to vibrate. The string has a natural or several natural frequencies at which it wants to vibrate. Your guitar string has a natural frequency at which it wants to vibrate. And that frequency is whatever it's tuned to. It's dependent upon the length of the string, the tightness of the string, okay, the material of the string, a number of factors. Who plays another instrument besides guitar, like a wind instrument? Okay, piano would actually be a string instrument, right? Okay. Who plays like a horn? Okay. Well, we have standing waves that are set up inside horns as well. They have resonant frequencies as well. They look a little bit different than what we see there, but it's the same kind of idea. Okay, we blow into that horn, we hear a sound. That's the resonant frequency of that horn. And we hear that because there's a standing wave set up inside that horn at the resonant frequency, the natural frequency. This is what it looks like. And this isn't the best diagram in the world, but you can see here that here, let me redraw it over here actually. Looks something like this, where we have waves going one way, we have waves going another way. They interfere to produce a pattern that looks like a bunch of bumps and then a bunch of spots where the wave isn't moving at all. These are what we call antinodes. Okay, the bumps are what we call antinodes. And then these spots right here that aren't moving at all are what we call nodes. Antinodes come as a result of constructive interference, and nodes come as a result of destructive interference. So why? What's the whole point of this? Well, in the end, we can understand why the guitar is making the note that it does. We can understand why the bridge vibrates at the frequency that it does, and why when we jump up and down at a very particular frequency, why the vibration of that bridge starts growing. We can understand, in fact, not only why the guitar string vibrates at the frequency that it does, but how to predict what frequency it's going to vibrate, or how to calculate the speed of the sound using this stuff of the sound in the guitar string. Fraser, question? No? I'm going to draw some pictures here of different standing waves that would be set up in a string that's fixed at both ends or that's attached at both ends. For example, the guitar string. Right? There's lots of other situations where it's fixed at both ends. Okay, the demonstration that I did for you. Okay, the bridge is fixed at both ends. The guitar is the obvious one, though, because we can see that and we can hear that. The first standing wave that would be set up would look something like this. It would have one antinode, and it would have two nodes. Here's my antinodes. Here's my node. Okay, one antinode and two nodes. You can see that I have it drawn here with a crest and a trough. with a bump and a dip. But in the end, we know the string can't be in both places at the same time. We know it's either at the top or the bottom or somewhere in between. We're just drawing the two boundaries. We know that if it's going fast enough, it appears to be in both places at the same time. But it can't truly be in both places. It has to be at the top or the bottom or somewhere in between. The next standing wave that would be produced here would be this one. Whoops, that's not the next one. Skip one. We had one antinode. The next one that would be produced would look something like this, where we'd have two antinodes. And that would occur at, well, we had 4 hertz, then we had, what was the next one that we produced in our demonstration? 8 hertz, so it'd be twice the first one. The next one's going to have 3 antinodes. It's going to look like this. And the next one's going to have 4 antinodes. And it's going to look something like this. Now, we're going to define the length of the string in all 4 cases as L. How long is a guitar string, Fraser? Any idea? Yeah, I suppose it does, eh? But it doesn't depend upon, it doesn't change much, right?
Well, you mean when it's not strung or when it's...
No, sorry, that's a good question. When it's strung. So the effective length of the string in terms of our sound that's produced has nothing to do with how long the string actually is. It has only to do with how long the string is when it's strung. In other words, from the tuner to the, what do you call the other end of the guitar? The bridge. Okay, so from the tuner to the bridge, that would be the effective length of the guitar string. And that's a little bit different for each string because of where the tuner is, right? Tuner's in a slightly different spot, right? But not much, right? How long is that, do you know? Maybe wouldn't be a meter, would it? Okay, about 75 centimeters, 3/4 of a meter. Okay. Of course, it's still going to work if it's a different length, right? It's just going to produce a different note, that's all. The length of the string we're going to call L, whatever that number is, 3/4 of a meter or 25 meters, it doesn't matter. Okay, the length is going to be L. Now what we're going to do is define, and this is the tricky step here, so bear with me on this, okay? We're going to define the length of these strings in terms of the wavelength. Let's draw a little wave over here, okay, a full wave over here. How much of a wavelength do we have right here in that first diagram? How much of a wave is that? Yep.
There's like a couple frets. I think it's the 12th one, and like a couple of right there on the what I'm talking about, where like you just put your finger over. Yeah, like a harmonic. Yeah, I think it's like where it's halfway, and then I think the string goes like that.
Okay, so you don't actually have to put your finger on it?
No, like you just hover your finger over, but you don't push down. And then when you strum, I think what the string does is like right at your finger, it's like halfway between.
Okay, so yeah, what's probably happening there is you'd be putting your finger like here. Or here, right? I expect that's what's happening. I'm not familiar enough with guitars and whatever to know exactly that, because I haven't done that and I haven't seen that or felt that, right? But I expect what's probably happening there is you're putting your finger on a node, okay? And you're probably feeling a bit of vibration there, but it's not changing the note when you do that, or it does change the note. Sorry. Oh, okay. Well, that makes sense actually then. Because then what you'd be doing is effectively changing the length of it, right? So all of a sudden, if you put your finger right here, you're changing it from 3 antinodes to 2 antinodes, right? So you're changing it from this diagram to this diagram, right? Does that make sense? I think that's probably what's happening there. But okay, so what is this again in terms of the wavelength here? The length is, it's a half a wavelength. Does that make sense? Okay, we're going, really, we just have a crest there, right? We're going right here. That's one half of a wavelength. This is a full wavelength. So what we have right there is a half a wavelength. Let's say L is equal to 1/2 lambda. L would be equal to what on this one? This is the easy one, right? Second one is L is equal to 1 wavelength, right? It's equal to lambda. This one's a little bit trickier. This one is, well, this would be half a wavelength. This would be a full wavelength. This would be 1.5 wavelengths. We can make it 1.5 lambda, but we're going to start seeing a pattern if we put it in fractions instead of decimals. So we'll say 3/2 lambda. Same thing. It's 1.5. But next one, here's a half. Here's a full. Here's another half. There's another half. That's going to be 2 lambda, right? Make sense? Or 4/2. Yeah. 4/2 works as well. Now, let's rearrange these to solve for lambda. In this case, lambda would be equal to 2L, right? The 2 goes up by multiplying. This one's easy. Lambda is equal to L. Here's lambda is equal to 2/3 L. The 2 goes up by multiplying. The 3 goes down by dividing. It becomes 2/3 L. And here lambda would be equal to 1/2 L, yeah. Now the final step in this process is to use the equation V is equal to F times lambda. Rearrange it. F is equal to V over lambda. V stands for the speed, right? F stands for the frequency. Okay, the note that we hear or the frequency of the wave that's being produced here. F is equal to V over 2L because lambda is 2L. If the speed of the wave is V and the length of the string is L, then the frequency of the first standing wave that would be produced is whatever that speed is divided by 2 times the length. Nick, you play guitar too, obviously? A little bit? No?
Like my dad.
Okay. How do you change the note? There's 2 ways to change the note on a guitar. Yeah, you do. I mean, don't make this too complicated, okay? I'm not looking for a really complicated answer here. How do you change the note on a guitar? What's one way? Okay, so you change the tuning on the guitar, right? Okay, you tighten the string or you loosen the string. When you tighten the string, the note gets higher. When you loosen the string, the note gets lower, right? Everybody's seen that before, right? Why? How does that change the frequency of the first standing wave that we hear? When we tighten the string, what happens? The speed of the wave gets, is your head up? Yeah, the sound travels faster through the string when we tighten the string. If V is bigger, then F is going to be bigger. What do we hear? A bigger F because the V was bigger. We made V bigger to make F bigger. What's the other way of doing it? Besides plucking a different string. Okay, what's the other way to do it? Shorten the string. How do you shorten a string? Put your finger on a fret. What are you doing there? You're cutting off part of the string. So now instead of the string being from the tuner to the bridge, now the string is from your finger to the bridge. Right? It's a shorter string. As you make L smaller, what happens to F? Bottom number gets smaller, this number gets higher, right? Put your finger on a fret, what do you hear? A higher note, right? That makes sense? Make sense? Okay, let's take a look at the second one that we see here, okay? We know that F is equal to V over lambda again, but this time lambda is L. So my equation would be V over L. We just sub in L for lambda. Let's do this one. F is equal to V over lambda. Let's sub in 2/3 L this time. That's not very neat, so let's kind of just tidy that up a little bit. It's the same thing as saying 3/2 times V over L. So V over 2/3 L is the same as 3/2 times V over L. And finally, the last one. I'm sorry? Yeah, it's the same thing. V over lambda for the last one. F is equal to V over 1/2 L, because lambda is a half L. which is the same thing as saying 2V over L. Now, what do we notice here? Maybe you don't notice anything. The first frequency that we see here is what we call the fundamental frequency. We might call it the first harmonic. It is a value of V over 2L. The second one that we see, we're going to call the first overtone, or the second harmonic. Notice the second one, F2, is twice the value of F1. Right? V over 2L, 2V over 2L, or just V over L. It's twice the value. And that's exactly what we saw when we did the demonstration at the beginning of class. The first one happened at 4 hertz, the second one happened at 8, twice that. This one we're going to call the second overtone. Or we're going to call it the third harmonic. What's its value? Well, the first one was V over 2L. The third one is 3V over 2L. So in other words, it's 3 times the value of the first one. In our demonstration, first one was 4, the third one was 12. 3 times the value of the first one. So we're going to say F3 is equal to 3 times F1. And finally, the last one, F is equal to V over 2L. We're going to call this the third overtone. We're going to call it the fourth harmonic. What's its value? Well, we had, for the first one, V over 2L. Now we've got 2V over L. How does that relate to the first one? A half V over L. Now we've got 2V over L. It's 4 times the value of the first one, hence the fourth harmonic. We're going to say F4, the fourth harmonic, is 4 times the value of the first harmonic. Make some sense? Now, we don't have a way of determining the speed of sound in a guitar string. Okay, we'd have to be given that value. There is a way, but we just won't see it. Okay. You can, yeah, absolutely. You can work backwards if you have everything else. Yeah. Okay, but if you need the value of V to find the value of F, the frequency, you're going to have to be given that value. Okay. If you are given that value, you can see how easy it is to find the frequency now, to predict the frequency of the sound that you're going to hear. The first frequency, the second frequency, the third frequency, and so on. Make sense? Okay, let's see what we got here in an example. It says a 25 centimeter long string is set in vibration. This is not a guitar, because a guitar is clearly longer than 25 centimeters. But you guys know that, you know, and as a kid, like a little kid, I remember this one time making this little musical instrument, or at least I called it a musical instrument. It wasn't specific C or D or E or whatever notes, but I remember taking this board and I put nails on this board. Okay, and I put the nails different distances apart, and then I put elastics between the nails. Okay, and then I remember plucking the elastics, and they would vibrate at a particular frequency. I didn't know anything about it. Okay. I didn't know why it caused the notes that it caused or the sounds that it caused. But in the end, what it was standing waves. Okay, one of those strings may have been about 25 centimeters long. The speed of the wave through that elastic maybe was 500 meters per second. That sounds like a lot. Okay, but the speed of sound in air is about 340 meters per second. And in a solid, it travels faster than it does through air. What are the first 3 possibilities for harmonics? So in other words, what's the first harmonic, the second harmonic, and the third harmonic? What are we going to hear here? What sound, when I plucked that elastic on the instrument that I made when I was 8 years old or however old I was, what were the sounds that would be produced by this little instrument? Let's draw it out. Here's the first harmonic. Let's not worry about the second and third one right now. Okay, let's just worry about the first one. The length of this is 1/2 of the lambda, the wavelength. And lambda is therefore equal to 2 times L. We know that frequency is V over lambda, but lambda is 2L. So the frequency of the first harmonic that I would hear would be the speed of the wave, 500 meters per second, divided by 2 times the length of the string. 500 divided by 2 times 0.25. 500 divided by 0.5. What's that going to give me? So the fundamental frequency that would be produced here when I pluck this elastic or whatever it is would be 1,000 hertz. What would be the second one? Well, there's a couple ways to do this. There's three that I want to find here, right? So we got the first one, we got to find the second and the third one. There's a couple ways that we can do that. The first way to find the second harmonic is to draw it out. There's the second. Derive the equation and analyze it the way that I just have. Is there a shortcut though? Isn't the second harmonic twice the first one? What would the third one be? Does that make sense? I wish that I was that I had some kind of musical background like lots of you guys do. I wish that I was better in music and I knew more about music than as much as, or at least comparable to lots of you guys, because to me this would make so much more sense if we have this musical background and we kind of see, we've heard these terms before and we, have somewhere to apply this to. Does this kind of make sense? For the music people and for other people for that matter? We all know what happens when we pluck a guitar string, right? We all know what happens when we put our finger on a fret, whether we play the guitar or not, right? We can see why. Okay, we got 5 questions up on the board for you here right now. I'd like you to take a look at those 5 questions. That's a little small. We'll try to make it a little bit bigger for you here, okay? Everybody take a look up here. I want to do question number 1 with you here now. It says, a 1.2 meter string vibrates at a fundamental frequency of 65 hertz. That's the first harmonic, the fundamental frequency. What is the speed of the wave through the string? The string is going to look like this, right? That's the first harmonic. If it was the second harmonic, it would look like this. Oops. If it was the second harmonic, it would look like this, but it's not. Okay, it tells me clearly that it's the fundamental or the first harmonic. We know the length of that is L. Let's derive my equation now for this. We know that L is equal to 1/2 of lambda, and therefore lambda would be equal to 2 times L. The equation that I use from here is the wave equation. V is equal to F times lambda, or F is equal to V over L. V over lambda, I should say. We know that lambda is 2L. So we know that the frequency here for the first harmonic in this string is V over 2L. We don't want to find frequency. We've already got it. So what do? Let's just rearrange it. V becomes equal to 2 times F times L. So I multiply 2 times my frequency of 65 hertz times the length of the string of 1.2 meters, and I should get about 160 meters per second, or 1.6 times 10 to the 2 meters per second. How many people got that question already? Good. So we're solving for a different variable than we did in our example problem and in our diagrams that we drew, but it's the same basic analysis, right? We're just solving, just rearranging it, that's all. Is that okay? Try the rest of them here now. We'll go over a couple more if we need to in a few minutes here, okay? All right, let's take a look at number 2 here now. It says a vibrating string has a frequency of 144 hertz. If the string is vibrating in 3 segments, what's the fundamental frequency? So we have 3 segments here, right? Which harmonic is that, by the way? Is that the first, second, the third, fourth, fifth harmonic? Which one is it? The first harmonic has 1 bump, right? The second harmonic would have 2 bumps. The third harmonic would have 3 bumps. So this is the third harmonic then, right? You want to find the fundamental frequency? What do you got to do? If we know that F3 is 3 times F1, then F1 is 1/3 times F3. It's a third of 144. Make sense? What does that work out to be? 48, is it? Okay, 48 hertz. How many people got that? Let's do number 3 while we're at it, actually. Okay, it's a little bit different as well. The frequency, the fundamental frequency is 354 hertz. What's the frequency of the third harmonic? Do we have to draw a picture here? We could derive an equation for the third harmonic, V over whatever L. But if we know the fundamental, the first harmonic already, then let's just multiply it by 3. 3 times 354, which works out to be 1.06 times 10 to the 3. It's kind of different ways about going about these, depending upon what exactly we have. Okay, let's keep going with 4 and 5 here for the next couple minutes, and then we'll go over those ones if we need to in a minute too. Let's take a quick look at number 5 before we flip the page here. This one says the frequency of the third harmonic is 1200 hertz. What's the frequency of the second harmonic? We know the third harmonic is 1.2 times 10 to the 3 hertz. We want to find the second harmonic. Now, we can draw pictures of this, and we can go, we can see it through the analysis that we've done, or we can take a bit of a shortcut here and say, wait, if the third harmonic is 1.2 times 10 to the 3, then the first harmonic would be 400, right? The third harmonic is 3 times the first harmonic. Now, we're not asked for the first harmonic, but it's probably the easiest way to find the second. If the first harmonic is 400, then the third harmonic is 1200. We were given 1200, we can determine 400. Now the second harmonic is going to be twice the first harmonic. So it's going to be 2 times the value of 400, which is 800 hertz. So sometimes we get a question like number 1 where we have to go through that entire analysis. And then sometimes we get a really quick, easy question like this one where we just have to multiply something by 2 or by 3. And then sometimes we have to do kind of something in the middle, like question number 5. Good news, if you're struggling a little bit with this, we got a little, oh my goodness, is that ever small? We got a little bit more practice here. We'll make this bigger. Okay, and you're only going to be able to see a few of the questions at a time, but we'll make this bigger so people at the back can see it. Okay, let's try this now, guys. We can see 4 of these questions. Can't see 2 of them. We can't see number 8. We can't see number 11. Let's try 6, 7, 9, and 10 first, and then we'll scroll down the page so that you can see number 8 and 11. Okay, let's see what you can do with these. Sorry, we're scratching number 9, actually. We're scratching number 9. 6, 7, and 10 first. Sorry, we can't do number 10 either. Sorry. If we can't do number 9, we can't do number 10. 6, 7 first, and then we'll take a look at number 8 once we can scroll down a little bit, okay?